Welcome, everyone. Thank you for joining today's session as we explore the architectural analysis and implementation of Dragonfly on Azure Kubernetes Service, or AKS. In this presentation, we will delve into how to effectively deploy Dragonfly as a high-performance, in-memory data storage solution specifically integrated within the Istio service mesh. Our discussion will follow a comprehensive architecture guide that bridges AKS with Istio and Iraqi Mesh to create a robust, scalable, and highly efficient infrastructure. Let us begin our deep dive into these technologies and their seamless integration. This visualization illustrates the significant performance disconnect between legacy software architecture and modern hardware capabilities, often referred to as the multi-core gap. On the left, we examine the legacy reality, typified by systems like Redis. Despite having access to 32 CPU cores, a single-threaded event loop creates a massive bottleneck. Only one thread is active, meaning 31 cores remain blocked and idle, which results in severely limited throughput. On the right, we contrast this with the hardware reality. Modern infrastructure, such as Azure E5 v5 instances, provides high core counts designed for massive parallel processing. When software is architected for multi-core utilization, every lane of the digital highway is open, maximizing throughput and ensuring full core utilization. The key takeaway is that legacy single-threaded models leave vast amounts of expensive compute power on the table, failing to leverage the true potential of today's high-performance server hardware. This slide illustrates a fundamental paradigm shift in system design, the shared nothing architecture. In this model, we move away from traditional shared memory structures to a system where each thread operates independently, managing its own specific slice of data known as a shard. By isolating data to individual cores, we effectively eliminate global locks. This is a significant breakthrough, as lock contention is traditionally the primary killer of concurrency and a major bottleneck in high-performance computing. To facilitate interaction between these isolated cores, we utilize a high-efficiency message bus for communication. Furthermore, the architecture leverages lightweight, stackful fibers to ensure 100% non-blocking operations. This combination of sharding, message passing, and fiber-based execution allows the system to scale linearly across modern multi-core processors without the overhead of synchronization. The shift from legacy data structures to modern, optimized designs is a cornerstone of our performance gains. On the left, we see the traditional linked list model, which suffers from significant pointer overhead and high metadata requirements. Because nodes are scattered throughout memory, this approach results in poor cache locality, forcing the CPU to wait on frequent memory fetches. In contrast, the Dragonfly dash table, shown on the right, utilizes a dense structure designed for sequential memory access. This layout is specifically optimized for CPU caches, leading to memory savings between 30 and 60%. Beyond the hash table itself, we have implemented dense set, a bitmap-based set structure that operates 10 times faster than traditional methods. Furthermore, we have introduced forkless snapshotting. By leveraging asynchronous serialization via I/O urine, we can maintain data persistence without the memory spikes typically associated with standard forking mechanisms. In this comparison of performance benchmarks, we see the clear throughput advantage Dragonfly maintains over Redis. As illustrated by the chart, Redis supports approximately 500,000 operations per second, while Dragonfly delivers over 4 million, resulting in 25 times higher throughput. This massive performance gain is driven by a fundamental shift in scaling strategy. While Redis typically requires clustering to scale out, Dragonfly utilizes a vertical core architecture to efficiently maximize modern hardware. Notably, Dragonfly achieves this scale while maintaining highly competitive responsiveness, with P99.9 latency remaining under 10 milliseconds. Optimizing the infrastructure layer for Azure Kubernetes Service, or AKS, requires a full-stack approach that aligns hardware capabilities with software performance. Starting at the foundation, we utilize Azure hardware via the ED-v5 and EBDS-v5 VM series, powered by Intel Ice Lake processors. This provides native AVX 512 instruction support, which is essential for SIMD optimizations. Moving to the OS kernel, we specify Linux 5.10 or higher to leverage IO_uring. This kernel feature is required for maximum asynchronous I/O efficiency. For the storage layer, we deploy Premium SSD v2 to ensure high throughput persistence without bottlenecks. Finally, at the application layer, utilizing the Dragonfly container allows us to fully capitalize on AVX 512 instruction support for optimized SIMD performance. By synchronizing these 4 layers, we create a highly tuned environment capable of handling the most demanding workloads.
The Dragonfly Kubernetes operator is designed to automate high availability and state management within your cluster. As shown in the manifest, by defining a replica count of 2, the operator automatically provisions 1 primary node and 1 replica node. The architectural diagram illustrates the operator's active role in monitoring the cluster state. Through continuous failover detection, the operator can identify node failures in real time. Once a failure is detected, the system initiates self-healing by automatically promoting a replica to primary status and reconfiguring the topology. This ensures the environment remains resilient and maintains the desired state without requiring manual intervention.
This slide details the network layer integration with the Istio service mesh, specifically focusing on how traffic flows within a pod. As shown, inbound traffic is first intercepted by the Envoy sidecar before being routed over localhost to the Dragonfly container. This sidecar pattern allows Envoy to capture and export telemetry data, providing essential insights into service performance and health. Most importantly, please note the critical configuration highlighted at the bottom, a mandatory port naming convention. To ensure Envoy activates the correct protocol filters, ports must be explicitly named TCP-Redis or TCP-Dragonfly. Adhering to this convention is vital for the proper functioning of the service mesh features within this environment. This slide outlines the security configuration for our environment, specifically focusing on mutual TLS or MTLS. As illustrated, the communication between Service A and the Dragonfly service is protected by an MTLS encrypted tunnel, ensuring that both parties are authenticated and the data remains private. To enforce this security posture, we utilize the Istio peer authentication resource shown in the configuration snippet. By setting the MTLS mode to strict within the Dragonfly system namespace, we implement a robust zero-trust policy. This means the system will reject any incoming plaintext connections, requiring all traffic to be encrypted. Furthermore, the Istio Certificate Authority manages the entire lifecycle of the security certificates, handling rotations automatically to maintain a high level of security with no manual intervention. The challenge in modern service meshes often lies in handling non-HTTP traffic. As we see on the left, a standard Envoy proxy typically views these protocols as opaque TCP blobs. Because it lacks layer 7 visibility, it cannot interpret specific commands or payloads, which prevents it from performing intelligent request-level routing for protocols like Redis or Thrift. Iraqi Mesh addresses this limitation by bridging the L7 protocol gap. As shown in the solution on the right, Iraqi provides the proxy with deep protocol awareness. Instead of seeing generic TCP data, the proxy can now identify specific commands, such as a Redis GET request, allowing for precise traffic management. By operating on the control plane, Iraqi Mesh empowers you to manage non-HTTP protocols with the same level of sophistication usually reserved for HTTP, enabling features like request-level load balancing and traffic splitting across a wider range of services. Iraqi Redis service provides advanced routing capabilities, specifically focusing on automated read-write splitting. As demonstrated in the configuration example, setting a read policy to replica allows the system to intelligently manage traffic based on the incoming command type. When a client request is received, Iraqi evaluates whether it is a read or write operation. Write commands are consistently routed to the primary node, while read traffic is automatically offloaded to the available replica nodes. This architecture ensures high deployment transparency, as the client only needs to connect to a single endpoint, while the service mesh handles the complexities of the underlying cluster topology. Operational resilience is fundamentally about ensuring system stability under pressure. To achieve this, we utilize 2 critical strategies: traffic mirroring and fault injection. Traffic mirroring allows us to duplicate live production traffic and route it to a shadow database for safe testing. By using a proxy to mirror requests, we can evaluate how new features or configurations handle actual user behavior without any risk to the production environment or the integrity of live data. Complementing this is fault injection, a proactive testing technique where we intentionally simulate errors, service delays, or failures within the system. This allows us to observe exactly how the application responds to stress and verify that our failover and recovery mechanisms work as designed. By identifying potential weak points through these simulated disruptions, we can build a more robust and reliable infrastructure capable of handling the complexities of a live environment. When evaluating scaling strategies, it is essential to distinguish between vertical power and horizontal complexity. On the left, horizontal sharding, the traditional approach used by Redis Cluster, often results in architectural friction. It is inherently complex, requiring frequent slot rebalancing and introducing significant network overhead as nodes communicate across the cluster. In contrast, Dragonfly leverages vertical scaling to provide a far simpler alternative. Instead of managing a sprawling network of nodes, you can scale by simply adding more CPU and RAM to a single machine. Because there is no need for resharding, this approach allows for the efficient management of terabyte-scale datasets on a single instance, streamlining operations while maintaining high performance. Observability provides essential visibility into the engine, ensuring we can monitor and maintain system health effectively. By tracking metrics such as memory usage and connected clients, we gain immediate insights into how the system handles current workloads. The diagram illustrates the interaction between Service A, Service B, and the multi-core Dragonfly engine, highlighting its capacity to process requests across multiple cores simultaneously. To provide this deep level of insight, we leverage three primary tools. Prometheus acts as the native endpoint for internal metrics, capturing data on memory and client connections. Kiali is used to visualize the service mesh topology and monitor MTLS status, ensuring secure and transparent service communication. Finally, Grafana provides comprehensive time series analysis, allowing us to evaluate performance trends over time and make data-driven decisions. To conclude, the modern real-time stack represents a paradigm shift in how we build and manage infrastructure. Its architectural superiority is rooted in a multi-threaded design that unlocks the full potential of modern hardware. This foundation allows for operational simplicity, enabling us to replace complex, fragmented clusters with the efficiency of vertical scaling. Beyond performance, this stack is both secure and smart. By leveraging Istio and Iraqi, we achieve robust zero-trust security and sophisticated Layer 7 routing. Most importantly, this architecture is future-ready. It is purpose-built to handle the extreme high-throughput demands of AI and real-time systems, ensuring we are prepared for the technological challenges of tomorrow.